I got an email from Eric like, man, I really, really want one of these. I really want to work on it. Is there anything I can do? I was like, well, okay, thanks for coming back. Yes, we'll send you one tomorrow. So yeah, this is an Eric Persing sound, and it is called I Am a Golden God. And it goes like that. So that was using 3 different synth patches. This is a tri-timbral synthesizer. So it has either 8 or 16 hardware analog voices, and you can divide those up internally into 1, 2, or 3 virtual synthesizers, which are groups of however many voices. You can just have one monosynth and like 4 voices doing a pad, another 4 voices doing an arpeggiated sound, things like that. And the whole front panel is designed to give you sort of knob per function access to all of the most performance-friendly aspects of the oscillators, the mixer, the filters, the envelopes, the LFOs, things like that. And there are buttons in the center console called panel focus that are basically pointing all the knobs at a particular one of your virtual, well, they're not really virtual, they are actual, but a particular one of the synthesizers that you have set up for a given patch. And so you can turn those on and off individually. So here's like just the bass sound. There's a lot of heavy detuning on that. It's supposed to sound like that. Let's see, go in here, we can change that around. Okay, here is just, okay, I see. Yeah, so it's 1 bass, and then the other 2 layers are a stereo lead. And I'm going to go from that gross excess to the simplest possible single sawtooth sound. And so that's 1 sawtooth oscillator, no filters, no envelopes, nothing fancy. The oscillators in the Moog 1 are a completely new design. Cyril Lance, our head engineer, actually got a patent for this last year. And we call it a variable core VCO. And so they are real voltage controlled analog oscillators. And most analog oscillators, like your classic mini Moog oscillator, is a sawtooth core. That means that the core of the sound is a voltage that charges up and it reaches a certain reset point, and then it resets to 0, it charges up and resets to 0. And it does that automatically as long as you keep feeding it with current. And however much current you feed it basically determines how fast it charges up and resets, which determines the frequency. So that's your basic wave shape. And then you can do other things to that basic wave shape to get different waveforms for your final sound. Another common oscillator topology is a triangle core, where you basically have a signal that it charges and it discharges in the same amount of time, and it charges and discharges. It makes a rising and falling ramp that's a triangle sound, or a triangle shape, and that gives a much more mellow sound. They're also, just because of the differences in how that particular circuit works, it means that it's easier or harder to modulate it in different ways. It does different things when you feed it into a wave folder or things like that. And so the innovation in the Moog 1 oscillators is that it does, it charges, it hits a comparator, it discharges, it resets, but we have very precise real-time control over all of the little subtleties of that. There's a microcontroller that is not, it's a real VCO. If you turn off the microcontroller and just feed it current, it keeps oscillating. But as long as that microcontroller is there, it is cycle by cycle controlling all of the charge time, the reset point, the voltage at which the core of the oscillator resets, or its minimum and its maximum, And we can control all of those things at the rate that the oscillator is oscillating. So every cycle we can change the charge time or change the reset voltage. And we can do that at audio rates. And so you have a real analog oscillator that you have really sophisticated ways to nudge and tweak and touch the waveform under digital control. And so the idea is that you get the best of the sound quality of an analog oscillator, but with a lot of potential for shaping that waveform that is novel, that we haven't seen before. So the basic sort of signature trick that this oscillator can do is that you can continuously vary the, there's some cute little OLED displays here in the oscillator section that show you, I don't know, I'm going to try something kind of crazy here. This is probably a terrible idea.
Do it.
There we go. If I hold it very stable. Oh my God! Okay. All right. Those little zigzaggy lines right there. That you just. Oh my God! It's like the Blair Witch Project over here. All right. Yeah. So. All right. You'll have to take my word for it. There are some OLED screens up there. I've ruined everything. I knew this would happen. Okay. Close enough.
So are you saying that the microcontroller is not clocking?
Correct. It is not clocking the oscillator. The oscillator is, the speed that the oscillator is going is determined strictly by voltage control. But it's measuring that oscillator at audio rates, and it's able to, so basically, like, let's say you've got the core of the oscillator, it's charging, and then it's going to reset when it hits some comparator voltage. The microprocessor can change that comparator voltage, like once a cycle if it wants to. Or it can.
Is that called some parameter? Is that a parameter name doing that?
Well, that particular one, I'm not sure about the. You might call it a reset voltage, a comparator threshold, something like that. But like for, a really specific example is that in the triangle mode of the oscillator, every cycle, it's setting the speed at which that triangle wave ramps up, and then it's setting the speed at which the triangle wave ramps down. And it's doing that, it's actually changing, some electrical values in that oscillator every, twice a cycle, once on the rising edge and once on the falling edge. And what that means is that you can continuously sweep between like a sawtooth wave with a really fast rise time and a slow fall time. If you slow down the rise time, you can morph over into a triangle, and if you speed up the fall time, you get a ramp wave.
Right.
And so you can continuously vary the waveform between those shapes. And that sounds something like this. So it's basically a triangle or a saw and a ramp sound pretty much the same as each other. Just the direction of time is reversed, and then a triangle in the middle has the least harmonics. So you get something like this. Oops, hold on. That is no longer my unit, so reinitial. There we go. So that's a sawtooth. That is not the right oscillator mode. There's a triangle. And then as you go to ramp, you hear those high harmonics coming back in. And that can do some really interesting stuff because adding and removing harmonics is, in a subtractive synthesizer, that's basically the filter's job. Your oscillator is going to put out the maximum harmonic content that it can, and then you take out harmonics later. The concept of adding and removing harmonics right at the source is almost like an additive synthesis concept. Although in this case, we're not combining simple sine waves, we are literally changing the rise time and the fall time of the waveform, which determines the harmonic content, or vice versa. But it lets you do some really cool stuff. You can do almost filter sweeps just within the oscillator itself. Filters are wide open. That's just one oscillator and just changing the wave shape. So there's a whole lot of sound shaping that you can do just within the oscillator itself. And of course we have 3 of them. And so the other facilities, hang on, I haven't even finished describing the first oscillator yet. So that's the triangle generator. And there's another mode that is a fast sawtooth. And so this is an even brighter. That's sort of the brightest waveform that you're going to get. And in that mode, this is kind of the most like a classic mini mode. It's just basically a sawtooth that does the thing where the harmonics change a little bit as you play up and down the keys, because the reset time of that sawtooth is a constant. And so as you play a higher and higher note, the reset time becomes a larger percentage of the waveform because it's a fixed duration. It doesn't scale the way that the ramp portion of the sawtooth does. But so that's your basic classic mode-y thing. But there's a really cool feature in this mode as well, which is that you can change what that fixed duration reset time is. And if you're comparing different vintage synths, you might find that like an Oberheim or sequential has a slightly different reset time because they use different transistors, they use different components than a Moog sawtooth oscillator would have. And that is a very subtle component of the distinctive characteristic of a particular synthesizer, but it is a component. So by being able to vary that reset time, you can actually, if you're trying to cop a specific sound from a particular other non-Moog vintage synthesizer, changing the reset time might get you there. And also, again, it's another way to do a really cool kind of filter sweep sound that's not really a filter sweep. As you start combining, more different sound sources together, it can be really nice to just trim off a little bit of the highs or just emphasize a little bit just by changing the wave shape before you even get into the filters, plural. There are 3 analog filters per voice, and I'm looking forward to getting to that soon. But just to briefly keep nerding out on the oscillators, so that's the saw and triangle generator. Each oscillator has 2 basic parts. It has that saw and triangle generator, and it has a pulse generator. And those exist in parallel. The pulse generator makes square waves and pulse waves. So that's your classic hollow sort of square wave tone. And of course, as you change the pulse width, a skinnier pulse wave makes a more of a nasal, sort of pinched sound with emphasis on the higher harmonics. That very, very tweezy sound is a narrow pulse wave, which is good for like, I don't know, clavinets and laser zaps and filter sweeps and stuff like that. And you can continuously crossfade between that pulse generator and the triangle generator, which gets you a lot of nice intermediate waveforms and lets you do a lot more blending and sort of harmonic motion within a single oscillator. So. Notice there's a little bit of a pitch warble there as I'm changing things like the pulse width and the wave shape, and that is normal anytime you do pulse width modulation and you're moving the duty cycle of an oscillator around as it's in motion. It's almost like the Doppler effect or something. You do get a slight change in pitch as you do that. So what I'm going to do right quickly is just add some modulation to this kind of chord that I have going. I'm going to add some pulse width modulation and modulate the waveform of the triangle just to hear how much the harmonics and sounds move around just from modulating the parameters of one oscillator right quickly. So that moment where the sound cut out completely, that was over-modulating the pulse wave to DC, to where it was 0% or 100% duty cycle, which you can't do from the knobs, but if you stack LFOs up, or if you push the pulse width with a modulator, you can modulate it all the way into silence. And that can be useful actually as a part of your sound design. You can make it so that a mod wheel turns off an oscillator completely just by modulating its pulse width into DC, or bring it back in. That's a fun trick you can do. So that's one oscillator. I think we've pretty much gone over all of the stuff that one oscillator does by itself. When you start to bring in more oscillators, that's when you get all of the relative tuning behaviors that you can get, and also things like hard sync and frequency modulation. So your three sound sources, among the sound sources, the three oscillators, each of them can be hard synced to the other oscillators, and you can choose, if oscillator 2 is going to hard sync to oscillator 1 or oscillator 3 can hard sync to oscillator 2 or oscillator 1. You can create a cascade where one is synced to the next is synced to the next. And your other sound sources include, and you can also do frequency modulation, where the actual signal from one oscillator is bending the pitch of another oscillator up and down at audio rate, and that does a lot of cool stuff, as I will demonstrate in a moment. And your other sound sources include a ring modulator and a very flexible noise source. So first of all, a little bit of detuning. So this is two oscillators, and they're just sort of, and I still got a lot of modulation going on. Let me turn some of that off. Okay, so those are two oscillators in unison. There are two different ways to detune the oscillators on the Moog 1. You can detune them in musical cents and semitones, and so that creates an interval that will track along the keys. And you can also do linear detuning, which is you're offsetting the frequency by a certain number of hertz, a certain number of cycles per second. And that offset remains constant as you go up and down the keys. And the interesting thing about that is that the way that musical frequencies relate to each other is the distance between any two notes isn't a constant number of hertz. It's got this logarithmic relationship where the frequencies double and double and double as you go up the octaves. So if you do a linear offset, that's going to sound, for the same amount of offset, for example, it's going to be a much bigger portion of a low note than it is a high note. A few hertz on a high note is a very small change, whereas a few hertz on a very low note, like a bass note that's like 50 hertz, a few hertz is going to be like semitones away. It's a huge change. But what that lets you do when you have two oscillators and you're detuning them by a certain amount is it gives you a beat frequency between them. So let me zero this back out and demonstrate. So there's a beat frequency of about maybe 2 cycles a second between those oscillators now, and that's what's doing that yom, yom, yom kind of sound. And if I play up the keyboard, that beat frequency stays relatively constant. This is an analog synthesizer. The tuning isn't perfect, so there's going to be a little bit of variation, but it's, broadly speaking, it's about the same. Whereas if I was to do a detuning the frequency in cents and semitones, then so I've created a slow beating down these low notes. And as I play up the keyboard, that beating is going to get faster and faster. And so that's traditionally, that's kind of the only detuning that you would have on a standard analog synthesizer is you'd be able to, if you wanted to get a slow beat frequency, it would only be the speed that you wanted it to be right around the note that you tuned it in on, and it would be slower or faster as you play around. And so I think having both of those options is really very cool. And another really nice thing about having musical and or cents and semitones versus linear detuning is that both of those knobs are mod destinations. So if you apply an LFO to the beat frequency knob, then you're doing linear FM. which has a completely different sound than exponential FM. So I'll do that right quickly here. So we'll talk about the LFOs more in a minute. There's no map in my head for how this goes. I'm just sort of flitting around. I think I'm roughly trying to make my way from left to right, but there will be detours along the way. So I've got an LFO that's now in audio range. It's currently at 200 hertz, and I'm going to apply it to the beat frequency of oscillator 2. Wow, awesome. Thank you.
Bass in this thing. No bass.
It's the resonant frequency of something in here for sure. I can just keep doing that for the next 15 minutes probably. So anyway, yeah, that's linear FM. And if I turn that off, if I apply the same LFO to the frequency knob, that'll be like an exponential FM. I don't know right off the top of my head how different it's going to sound, but it's different, and especially as you combine more layers of these things, the differences, if they're small to begin with, they kind of magnify. And with FM type sounds, the modulation index, the depth and frequency of the modulation has a huge effect on the tonality and on the tuning. So it's possible to dial in sounds like this that are musically playable, and you tend to get some nice like grindy guitar kind of sounds. It's good for like buzzy leads, things like that. But this process of getting all the ratios just right and getting it dialed in to track the keyboard exactly is like more fiddly than I want to stand up here and go through, and you know, it'll just be a lot of like sort of things. Yeah, that wouldn't do bad. All right, so yeah, that's the FM piece, and now one thing about that is that I got that nice tonality, but that's not in concert pitch anymore, which is typical for analog FM sounds. So I would have to, if I bring in another oscillator that's just normal, I'll have to tune them to each other, which I fooled myself here because I was in the middle of assigning modulation. All right, that gets back to what I was saying about really dialing this in musically as like this fiddly process of sitting and making small adjustments, and so I won't do that right now, but we will press on. All right, so that's two oscillators. Third one sounds a lot like the first two. So that brings us to the other sound sources, which are a ring modulator. And the ring modulator is an analog ring mod that is fed by two of the VCOs. And you can pick which two. It's like 1 and 2 or 2 and 3, I think, are your options. And what that does is it's modulating the amplitude of one of those oscillators at the frequency of the other oscillator. And if you modulate amplitude at an audio rate, you get AM amplitude modulation, which creates tones that weren't present in the original signal. It's the tone of that signal, going away and being present at an audible rate. And so ring mods are good for, you can get really easy sub-octave from them if your oscillators are tuned together, or you get really interesting sum and difference frequencies as the frequencies of those oscillators change relative to each other. So you can already hear that tonality. It's kind of got like a buzz to it, whereas the oscillators that are feeding it sound, they're just a pure tone. The ring mod has an edge to it, which is one of those frequencies being amplitude modulated by the other, and you get kind of a sub-bass tone out of it. And as you change the frequency of the oscillators around, you hear all these interesting sum and difference frequencies happen. So at the end, those oscillators were in unison, and that's why all those different harmonics kind of collapsed down into this one pure tone, because they were in phase and in sync with each other. Sync. I almost forgot about hard sync.
I have a question.
Yeah, absolutely. And interrupt me anytime. Anybody has questions, shout them out. It's fine.
In this sound, the ring mod you're playing, is that one of the three sections? Tri-timbral? That's one of the engines?
Correct.
Okay.
Yeah, so that particular sound, if we like that, so we can save that and then add two completely unrelated analog synth sounds on top of that in one performance. That could be like, a pad with a bass and a lead on top of it.
Right, they could be layered or split, and then the splits are completely flexed?
Correct. Yeah. So that was actually, it wasn't just one voice. That was a chord. That was three voices. And so yeah, your number of hardware voices limits how many splits or layers or whatever you can have. So that was, that chord took up three voices. That means on this instrument, I still had five other voices that I could use, like one for bass and four for, some lead or arpeggio or something like that.
But they're assignable. You reserve three for that first engine?
Correct. Yeah, absolutely. So the way, the way the preset structure is set up, again, I'm kind of lacking my overhead camera, so basically you have synth 1, synth 2, and synth 3, each of which is the whole enchilada, all of the aspects of a voice you get times however many hardware voices, and to create a synth sound, a timbre within a preset, you set up your voice however you want, and then you go to the polyphony settings and say how many voices of this sound do I want. And do I want it to be mono, do I want it to be in unison, etc. And then you can save that, and you're good, you're done. You can then go over to one of the others and set up another sound, say how many voices you want it to use. And then, as you said, set the split, the key range, whether they overlap, whether they're, one's on this side and one's on that side of a split, and so on. Yeah, so you can set
the polyphonies props themselves. So when
correct.
they look themselves.
Within the pool that you've defined for that voice, rather than robbing from one of the other timbres. That's right. Yeah, early on we did have that problem where you'd hold down a chord and you'd play some licks over here, and then one of your chord notes would disappear because it got stolen by the notes you were playing. Not musically useful. So it just, we made sure it does not do that.
You went tribal.
we went in for sure. All right, so hard sync real quickly. Hard sync is a really classic sound that most analog synth aficionados know, and it's that's your classic hard sync sound. And what that's doing is the oscillator that I was tweaking the knob of, I was raising its frequency, but at the same time, every time the first oscillator resets its cycle, every time it does one cycle, it hard resets the other oscillator that I was tweaking, And what that does is it imposes the frequency of the master oscillator onto the synced oscillator. So it's trying to do its own thing, it's trying to play a really high frequency, but it's being reset every time the master oscillator is, so it's forced to produce that frequency even as it's also trying to race ahead and do its own thing. So you get this really nice superposition of the frequency of the master oscillator and the frequency of the synced oscillator, which presents itself as typically higher harmonics and kind of ringing overtones. And because of the nature of these things, you actually do start to hear the harmonic series of overtones popping out as the synced oscillator frequency increases. And of course you can combine that with the ring mod. Ring mod and hard sync.
And can that be driven by LFO?
Oh, of course. Yeah, I guess I should say every knob on the front panel is a mod destination. And so the way you set up modulation, I'll go ahead and do that right quickly. So the LFOs are all clustered over on this side, the envelopes are all clustered over on this side, and you've got other assignment buttons for things like the pitch wheel, the mod wheel, the XY pad. There's an XY pad that's also pressure sensitive on the left-hand controller here, right by the pitch and mod wheels. And so, for example, I'll assign the pad x-axis to the hard synced oscillator frequency, and I'll assign the y-axis to the ring mod oscillator frequency. So you do that. It's really simple to assign modulation on the one. So there's a button here for pad X. You press that button, and then you grab the knob that you want it to modulate and just turn it. And so, and how far you turn the knob sets the depth of modulation. So I've got that in there. Now I'll go to the y-axis and set it to modulate the frequency of the oscillator that's feeding the ring mod. And now we have this.